We did a computational analysis of it with colleague Kawamoto and Professor Andrade at Caltech. So the objective of this talk is to study this last part of this curve of evolution of the strength or mobilization of the friction angle. So at this part we call it like the residual strength, which is pretty well known by now that it is independent of the interparticle friction coefficient. But it happens to be at critical state as well. So since the residual strength is independent on the interparticle friction coefficient, it should depend on something because it changes from material to material. So we believe and we want to study the dependency of the critical state on the morphology of the particles. But at critical state we also have these other parameters, and the entire models and books have been written in terms of these parameters. This critical state line slope, lambda, and gamma, which is the intercept of the critical state line at some arbitrary pressure. So we want to relate these three parameters to morphology, to study the effects of morphology in these parameters. And to do that, we want to use a method developed by us in our lab, which is a kind of DEM scheme. So we need first to calibrate it with respect to a real experiment, with respect to the real thing, and here it is. So we use this experiment from these guys in the University of Sydney. It's a 2D infinite shear test. And this is the real setup. They have three different sizes of particles, two belts. The belts run and shear the material until it reaches critical state. And here is our numerical setup. We also use the same number of particles, same distribution, three different sizes, and we kind of plot the same curves or values for this. The diameter, average diameter, and the porosity are exactly the same, but we don't want to calibrate for them, but for this curve here. So this curve is the shear strain rate, the normalized shear strain rate across the section. And this is the experiment, the blue one, and the cyan one is the one that we got after calibration. And here are the parameters that we use once we calibrated the method: particle density, particle stiffness, interparticle friction, global damping, and no contact damping. So we have calibrated the method with respect to this and with respect to a real experiment. And now we want to use it to do real shapes. So we now want, once we get this calibration, want to test it with real shapes. So here they are. We have these real cross sections coming from Caicotzoid. It's a kind of sand that they have in France. So we get the X-ray CT scan and we make it into level sets. And we combine this level set mathematical technique with a classical DEM technique. And these are cross sections of those real particles. And then here we're running the shear experiment for this. So it works, it seems to work, it is calibrated. And now we can dig into the relations between particle morphology and the critical state. So we use these pretty well-known parameters, sphericity and roundness. Sphericity is related to the diameter, to the order of the diameter, and roundness is related to the order of the diameter divided by 10. And here's the table of particle morphology in terms of these two parameters. So we build our own table. We use these real shapes. We have given names to them. And we also use idealizations that have similar roundness and sphericity. And we also want to study the effects of idealization, how different is doing the real thing or the idealized thing. So here are the results. We plot the results for the different critical state parameters, lambda, gamma, and the critical state friction angle. In terms of this parameter called regularity, the particle regularity is nothing but the average between roundness and sphericity. So roundness plus sphericity divided by 2. And we have ordered the real particles and the idealizations in terms of their value here with respect to the regularity. And here are the results. This is the linear fitting. So the line corresponding to the real particles is different to the line corresponding to the idealized particles, except perhaps for the fielded particle. The same thing for the critical state line intercept gamma. We have different lines, different slopes, except, once again, for the fielded particle. And for critical state friction angle, we have something like the slopes here are kind of similar, which means that the idealization for the critical state friction angle isn't as important as for the other parameters. Here are some previous results from real experiments years ago with real particles in a real lab by Cho, Dodds, and Santa Marina. So they plot the critical state friction angle, the intercept, and the slope in terms of roundness, because they claim that the critical state friction angle depends only on roundness and not on sphericity. The same thing for the intercept, and they claim that the slope doesn't depend on roundness nor sphericity. For them, this is almost a constant, and that's why they plot it against regularity. Let's see what we get. We want to dig deeper, so we plot these contour lines. We plot the values of, in this case, gamma, the critical state line slope, in terms of sphericity and roundness for the particles that we've got, and the real ones and the idealized ones. And so we can see here that the behavior is in fact different from idealization to the real thing. And also it seems to depend on roundness and sphericity. Same thing for gamma, the intercept, which doesn't seem to depend that much on sphericity, but the behavior from real to ideal is different, in fact. And here we have the critical state friction angle, where the behavior is kind of similar in the two cases, and it seems to depend on sphericity and roundness. These for the particles that we're showing here. So we want to summarize this information. And the first thing that we did is we have introduced a new method, LS-DEM, level sets DEM, which enables us to do real shapes, to include real shapes into a classical DEM scheme. Then we have applied this new technique, LS-DEM, to study the relations between grain morphology and critical state parameters, as well as the effects of idealization. So from there, we know that, for instance, compaction becomes less pressure dependent as grain regularity increases. So the more the regular the more regular grain is, it is less pressure dependent in order to have the collar rate packed. As a consequence of this, we have this point B: regular grains reach critical state at a more compact stage than irregular grains. Also, we have learned that more regularity implies less strength. So if we have packings with more regular grains, these packings will tend to be less strong than the other ones. So regularity matters. And finally, that the critical state friction angle shows less sensitiveness to idealization among all the parameters studied. So in general, idealization matters. And we have this table here summarizing all that we've learned from the study. For instance, which are the most sensitive particles for each parameter, the least sensitive particles, and the idealization, what's the difference between the idealization and the real thing. And here, what we have similar and different to the real study by Cho and the others. So we coincide, we agree with them for gamma, so mostly depends on R, but we disagree for lambda, where they claim that it only depends on roundness, but we see dependency on sphericity as well. And we see dependency of the critical state friction angle on both, the sphericity and roundness, and not independency. But I have to say that their studies in a real setting with three-dimensional grains, and this is a two-dimensional study. So once we take this to the three-dimensional thing, these results might change. And that will be
yes, please. So how many realization did you? How many random realization did you perform in a simulation on per element shape?
element shape.
Like each element shape, you run one simulation.
Once we did many simulations, like 5 for each one, and we compared the results, and they in general were pretty much the same each time.
How did you control the size distribution for different shapes?
We followed more or less the same as the original experiment. For instance, in the original experiment, the one with discs in Australia, they have 3 different sizes of discs, right? They do it because they're using this and they want to avoid crystallization. They don't want it directly to crystallize. So we did this pretty much the same thing, but with arbitrary shapes. We took these shapes and we made it into 3 different sizes, more or less following the same ratios that the original ones had for each one, idealized and real one.
Okay, just it looks like you're drawing lines, but the trend is not so strong. I mean, just be careful.
For the trend is pretty strong for real ones. That's why I'm plotting here. I'm including R squared, which is the goodness of fitting, as you may know. It's 0.95. So that means pretty strong, sorry. And in the case of the idealized particles, it isn't as strong.
Okay, that's why I thought the number.
So that's because in the case of the idealized particles, we have more corners and things like that. So we tend to have more kind of crystallized behavior.
I have a question. Is it not reasonable to change also the interparticle friction if you change this roundness? Because if you change the roundness, you also increase the roughness. Then in reality, the friction is also different between such a particle.
No, the claim is, and it's been proven in the lab and in numerical simulations, that at critical state, these parameters do not depend on the interparticle friction in general, unless you have like almost 0 interparticle friction. Then you start to see weird things with very low interparticle friction.
Yeah, I agree. It has not any effect on the critical state because you are interested. But in the reality, maybe we should also change the interparticle.
Yeah, in general, yes. But in this case, we're still in critical state. We didn't take that much.
Okay.
So we focus on rawness and sphericity, and the next scale, the bigger scale is sphericity, the next scale is rawness, and the next scale will be the interparticle friction. But since we're studying critical state, we didn't include that.
I have 2 questions. The first one is, how good can level set methods approximate shapes with singularities and very flat surface?
It can be as good as you want. It depends on the grid. And in fact, my colleague grid is going to be talking.
Differentiable surface edge, you can approximate with 11%.
Say it again.
Singularities shape, very easy.
It can approximate, it depends on you, but it will make the computation heavier and heavier, right? Yeah, but it's up to you.
The second question, when you define critical state, have you considered the unique anisotropy? Have you considered anisotropic structure, which, like the Professor Tapari yesterday presented?
Well, we're focused on shape, right? So we don't want to make a whole mess of different shapes, but study particular shapes.
But then it may not critical state, actually. Even it has constant space and constant volume.
It might, no, you have to compute the parameters once you get to critical state. So you let it evolve, and you get to critical state. Otherwise, you cannot get lambda and gamma. Those are parameters that have to be computed at critical state, right? So you let it evolve till you reach critical state.
I think one last question.
Yeah. Thank you for the nice presentation. The interparticle friction coefficient you use is 0.25. That is equivalent to interparticle friction angle of less than 15, and more or less 14.
Mm-hmm.
But the data shown in the Santa Marina paper is about real solid soil grains. So the interparticle friction angle is typically at least 25. So how would you make a quantitative comparison between these two?
Well, we aren't doing a quantitative comparison. We are doing a qualitative comparison.
Is there any you chose that pick that number 0.25?
Yeah, we calibrated our numerical method with respect to the original experiment, but the one done by the guys in Australia. That's the one that provided the calibration, and then we run it for that. Then the results from the Cho and Santa Marina paper, we use them to see if we get the same trends and how different and how similar they are, qualitatively, not quantitatively.
Okay, due to time limit, thank you, speaker again.